Hello, everyone, and welcome to our talk on NVMe Computational Storage. There will be two of us that are presenting today. First, I'm Kim Malone from Intel, and I am a co-chair of the NVMe Computational Storage Task Group. And my co-presenter is also a co-chair of the NVMe Computational Storage Task Group, and that's Stephen Bates from Eideticom. We're going to be talking about a couple of things today. First, the architecture for NVMe Computational Storage. Next, we'll be talking about example flows. We will summarize the NVMe changes for computational storage. And finally, we'll tell you a little bit about the NVMe Computational Storage Task Group. So first, let's talk about the general architecture and the major architectural components. So as you can see in this diagram, there's two different kinds of namespaces. On the left, you can see the gray box that has compute namespaces, and those are new with this technical proposal. I'll talk more about those in a minute. In the middle, we have subsystem local memory, and then on the right-hand side, we have NVM namespaces, and those are the NVM namespaces you know and love already. So some of the key things to know about this architecture is that the programs operate only on data in subsystem local memory, which is the light blue in the middle. And that includes program input and output. So data is copied between subsystem local memory and host memory using new NVMe commands. And the details of the commands to copy data between subsystem local memory and NVMe namespaces is still being determined. We're definitely working through the details there, but we haven't finished that quite yet. Another thing to note here is that within each compute namespace, there is a unique set of programs and little indexes to put the programs into. And we'll talk more about that later as well. So one thing that is newly introduced by this technical proposal is namespaces for computational programs commands. So this command set, this is to back up a little bit, this is technical proposal 4091 in NVMe, and that proposal introduces a new command set and a new namespace type. And that new type is a computational namespace. So a computational namespace is an entity in an NVMe subsystem that's able to execute one or more programs. That namespace may have asymmetric access to subsystem memory. So some computational namespaces may have access to certain memory and others may have access to different memory. And each computational namespace may support a subset of all program types. And as I'm sure you've been getting from the way I've been talking about it, programs are managed on a per computational namespace basis. So let's talk a little bit about programs. So I've been calling these offloads programs, and that's a term that we've been using in NVMe Computational Storage. And so programs are invoked and used in a standard way. And conceptually, they're similar to software functions, so in that they're called with parameters and run to completion. As I mentioned earlier, they operate on data on-device memory. They run on compute resources, and more specifically on compute namespaces. The programs may be either in hardware or software, and a program may only be able to execute on a subset of the compute resources, or another way to say it is a subset of the computational namespaces in an NVM subsystem. So there's two main kinds of programs that we have in NVMe CS. The first is a downloadable program, and the second is device-defined programs. So one of the things that we determined was important was to support both of these kinds in this technical proposal, so both device-defined and downloadable. So device-defined here is a term we're using to refer to fixed programs that are provided by the manufacturer, and they're functionality implemented by the device that's callable as a program. So that could be compression, decryption. It could be implemented in an FPGA or in an ASIC or some other way that the device provides but isn't changeable by the host. The other kind is downloadable programs. So downloadable programs are programs that may be loaded to the computational namespace by the host. And I'll talk a little bit more about what types of downloadable programs we're going to support in a second. So the type that we're going to support in the first release, which is TP4091, is eBPF as a downloadable program type. So allowing downloadable programs provides a lot of flexibility to what a device can do. It allows you to process complex formats, maybe work on emerging applications where you might want to implement something in eBPF first and then in an ASIC later. And it allows portability from existing applications. So eBPF in particular is vendor agnostic. It's been around for a while. It's fairly well understood. There's existing ecosystems and tooling, and sits under the Linux Foundation. So this is why we have gone with eBPF as the first type of downloadable program with NVMe CS. And at this point, I will hand it over to my co-presenter, Stephen.
Thank you, Kim, for that great overview of where we're going with NVMe Computational Storage. So I'm going to kind of take a step back to the higher level and take some of those constructs that Kim has introduced and feed them into a couple of example flows to give you a sense of how exactly NVMe Computational Storage is going to work. So Kim, if you don't mind jumping to the first example, thank you for driving the slides. So, I think a very important thing to think about is, as Kim mentioned in her section, we're taking some of the architectural constructs of NVMe and applying them to a new, for want of a better word, type of namespace. And a namespace in NVMe is a logical construct. Up until now, it's been storage-centric in nature, but there's really nothing inherent in a namespace that means it has to be storage-centric. Oh, we just jumped back a slide. There we go. So we're introducing a new command set that will apply to a new type of namespace, and those are compute namespaces. And like Kim said, they can execute a variety of different programs. Some of those may be downloadable. Some of them may be fixed functions. And these namespaces will be able to execute one or more computational program against data that exists somewhere on the NVMe or the NVM subsystem. And before I dig into this diagram, I just want to kind of point out a couple of things. In an NVMe device, we always communicate from the host through an NVMe controller. In this particular example, we're just looking at a single NVMe controller in a subsystem, but the same kind of constructs will apply to multi-controller systems, which is very useful for things like multipath and high availability. So the reason why we've done things in a certain way is because we have to be cognizant of the fact that computational programs will have to work in both single controller and multi-controller environments. And that feeds into some of the decisions that are made. As Kim pointed out, NVM subsystems can contain a number of namespaces of different types. In this particular example, we assume we have compute namespaces. We have a construct called subsystem local memory, which I'll talk about in a minute. And then we have NVM namespaces, which are kind of classic places where we store data. And what we want to be able to do with the computational programs TP 4091 is to allow the execution of programs against data that's already on the device. I mean, one of the key rationales of computational storage is to reduce data movement. So what we want to be able to do is process data that's already living on these NVMe devices, whether they're solid state drives or NVMe over fabric arrays or something else. Doesn't matter in the sense that all of those types of products should, in theory, if they want to, be able to store to support these computational programs. Now, the way in which we do work is also aligned with the way NVMe or NVM Express works from an architectural point of view. i.e. the host issues commands against namespaces behind a controller. So in this diagram, we actually have three commands being executed, and I'll kind of walk through those in turn. There's the A command, the B command, and the C command. And like NVMe everywhere, these commands are typically 64-byte completion queue entries that we place on a queue somewhere in memory, and that memory could be on the host or on the device if we're using controller memory buffers. And then we ring doorbells, and the device supports multiple queues, and it will process those queues not necessarily in order, and post completions when those commands are done. And computational program command set is no different to NVM command set in that regard. We construct things that we want the host to ask the controller and the subsystem to do, and then they do them. So in this particular case, we have a bunch of data in the form of a database that could be in something like CSV or something more complicated like Parquet, sitting on a formatted NVM namespace. And the first thing that we'd like to do is get that data into subsystem local memory. And we won't go into all the details of subsystem local memory today because that is still being developed by the NVMe technical working group. But there is a mechanism that will exist to move data from the NVM namespace into subsystem local memory. And we do that because NVM is typically not byte addressable. You can't really run a program against something that has the kind of granularity that non-volatile memory has. So what we want to do is put the data that's stored on the flash or some other non-volatile medium and get it into something that's more memory-centric in nature, and that's subsystem local memory. Once we have our input data in subsystem local memory, we can execute a program against that data. And so that is the B command in this particular example, where the host tells the NVM subsystem through the controller, I'd like you to execute program at ID 0, which on this particular namespace is a filtering program. Execute that program against data that's stored in this region of subsystem local memory. And I'm not going to go today into all the details of how we specify that, but that will be specified in the standard. And then you might also say, and I'd like you to put the results somewhere else in subsystem local memory. And in this case, we execute a filtering program that finds all the entries in our database where the name exists in the state of New York, and it puts that into a different part of subsystem local memory. And that could be run via an eBPF program or even a hard-coded program, a fixed function or device-defined program if you wanted. Once that program has executed, you have a few different choices in what you'd like, what you're able to do. In theory, you could take the output of this program and pass it to another program, and we have an example a bit like that on the next slide. But the other things you could do is write the output data back to an NVM namespace. So you could say, I want to take my output and put it somewhere else on a non-volatile memory namespace. Or you could move it back to the host. And in this particular example, we move it back to host memory so that an application on the host can take advantage of this filtered data. In that case, we execute a read subsystem local memory command. And like I said, the exact format of that command is still a work in progress. But ultimately, what would happen is the NVMe controller would ensure the data is moved over the relevant NVMe transport back to host memory and post a completion queue entry when that is done. And at that point, the host is able to look at that data in its memory space and pass it to other programs, pass it to other accelerators, move it out onto the network, et cetera, et cetera. The key thing here is we've managed to keep all the processing and data movement confined to the NVM subsystem, except when we want to get the output data out. So we see a large reduction in data movement, which is one of the key objectives of computational storage. So Kim, if you don't mind, can we go to the next slide? In this next slide, we actually start chaining some programs together. So I'm not going to spend as much time on this particular example, but here we just assume the data on the flash or the non-volatile memory is encrypted. So we can't filter the data because it's not in plain text. We can't read the entries in our database. So the first thing we have to do is decrypt the program, and that is what happens in the B step of the B command of the 4 commands we execute from the host against the subsystem. We would probably pass in some kind of key in order to allow that decryption to occur, or the key might already be on the NVMe subsystem. That's a little bit outside the purview of today's talk. And we actually would request the decrypted data, so the output of the decrypt program, be put in subsystem local memory. At which point we're kind of back to where we were in the previous example. And now what we can do is execute our filtering program on that decrypted data, which is now in plain text, get our filtered results, and in this case, perform the same last command as we did in the previous example and copy that data back to the host. So again, this allows us to do multiple steps via host control. But think of the host as the conductor of the orchestra. The work is actually being done on the NVM subsystem behind the NVMe controller. So Kim, if we could go to the next slide. I want to talk a little about what this means in terms of changes to the NVMe specification. And that is really the ultimate output of the work of TP4091, is to provide an update to the NVMe standard documentation to support this new command set. So in TP4091, on the left here, I'll talk about the right in just a minute. This TP is entitled Computational Programs, and it's going to specify a new command set for computational namespaces. So the commands that are associated with these namespaces are, as you might expect for a computation namespace, not your typical read, write, erase, trim type commands. They're much more aligned with computation. So we have commands like execute program, load program, activate, which we didn't get into today, but we can talk more about it another date. And then another very important command which maps address spaces into the computational namespaces address range. Again, we don't really have time to go into this today, but a very interesting command called create delete memory range set. Obviously, we need to learn about what these NVM subsystems are able to do from the host. So there's support for new identify controller structures for these namespace command sets. There's log pages that we're introducing to support computational programs. And so we will see a new section in the NVMe standard to support this new command set, and also some updates to the other specifications so they can refer into this new command set. Now, the other TP that has emerged as we've worked through computational programs is the subsystem local memory TP, which is 4131. So we don't have a lot of time to go into this one today, but it also introduces a new command set for memory-centric namespaces or memory namespaces. This TP is still very much a work in progress. So the commands that we expect to have for this subsystem local memory command set are TBD, but they will facilitate things like reading from and writing to memory namespaces from host memory, probably supporting copying from things like NVM namespaces into these memory namespaces and vice versa. And there will be associated identified data structures and log pages to facilitate all of that. So quite a lot of work happening. I think this is very exciting work and very interesting work. And it should make the NVMe specification even more powerful and successful than it already is. Kim, if you don't mind, let's jump to the next slide. So this is kind of our call to action slide. If you're interested and excited about anything you've seen here today, and you want to get involved, please come join us at the Computational Storage Task Group within the NVM Express Technical Working Group. You can come and work with me and my excellent two co-chairs, Kim, who has already spoken today, and Bill Martin from Samsung. You know, the objectives that we have are to define this architecture for 4091 and to take 4091 through these steps of technical development to ratification, where we integrate into the public standard. And obviously also we are seeing other TPs emerge as we work through 4091. We have a very strong membership. Right now we're sitting at 211 members from 47 companies. Those companies include a range of vendors and end users and people in the, some of the supporting standards bodies in the industry. So please do come along. If you're interested in getting involved, please follow the steps outlined and join the task group, assuming your company is an NVMe member. And if your company isn't an NVMe member, it should become an NVMe member. The task group meetings are right after the technical work group meetings on Thursdays, 9 to 10 a.m. Pacific time. And we hope to see you there. So Kim, if you don't mind jumping to the last slide. So that concludes our update on NVMe computational storage, computational programs. Like I said, this is a really exciting space. I think it takes NVMe and storage in general in a very exciting direction. If you've enjoyed this session, please rate it highly. And thank you very much for your time. Enjoy the rest of your day.